So we are ahead of schedule by one class meeting. And at the end of our last class, we talked about what we were going to do about that. And I believe it was decided that we were going to have a day where we were going to work problems and I was going to help you with your homeworks and all that kind of jazz. Today is that day. I have uploaded another homework set on the power relationships and all of that kind of stuff. It is on Moodle. So where do you guys want to start? Number 4 from homework set number 5. Sure thing.
We not have another section.
There is another section on power, like how power is practically measured that I want to talk about. But I didn't have time to prepare the notes for the 2-watt meter method. And also there's not going to be any problems or anything associated with that. It's literally just how you go about making those measurements and all that kind of stuff in a practical sense. So with regards to the material that's going to be like on the exam that you'll be tested on, we're effectively done. So let me open up that homework set.
And it's next Tuesday, right?
The exam is next Tuesday, and this homework set that I uploaded is also due next Tuesday. So you've got a week to get all of this stuff figured out. Where is ELET? There we go. All right, so Bailey has asked about problem number 4. So I'm just scrolling down here to look at it. Let me get my computer in a way that I can write on things. So we have a delta-delta system, and we are asked to determine the line voltages at the source if we know the phase current in the load. Okay. So the first thing that we're going to have to do to be able to figure anything out here is figure out how to draw our single phase equivalent circuit for this thing, right? Well, actually, let's talk our way through things here and figure out some stuff from the jump. All right. So we know the line impedance and we know the load impedance. So we know this quantity and we know this quantity. We are given the phase current in the load. So we know this quantity. So how might we go about determining our line currents? Anybody have any thought there? Because right now, the only piece of information that we have for our single phase equivalent circuit is literally ZW. So I'm trying to figure out other pieces of information that we could use, because our ultimate goal is to figure out what this voltage VAB is. Once we know that, we're good for the other 3 phases. Right. So what Jack is suggesting is that since we know this current ICA is simply IAB times a factor of 1 angle negative 240 degrees. In previous problems, we performed Kirchhoff's current law at this node, and we found that our line current IAA is equal to our phase current IAB minus our phase current ICA, which is the same thing as IAB times √3 angle negative 30 degrees. So do the math. I mean that literally quite literally, right? So if we have IAB times 1 minus 1 angle negative 240 degrees, put that in your calculator. Oh, okay. So no, because the C phase is 2 lagging behind the A phase, right? So the B phase lags the A phase by 120 degrees. The C phase lags the B phase by 120 degrees, which means the C phase lags the A phase by 240 degrees. Absolutely, yeah. So if we were trying to figure out this phase current here, IBC, this one is lagging by 120. ICA is lagging that one by 120, so it's a total of 240 degrees lagging. Okay, so we now have enough information to figure out what IAA is, so let's write that down here really quickly. So 15 angle 40 times √3 angle negative 30 is going to come out to be 25.981 with an angle of 10 degrees amps RMS. So if we were looking at our single phase equivalent circuit, here's A, here's VAN, here's ZW, here's a ZY, we now have this ZW and this current IAA. So ultimately, what we're trying to figure out with our single phase equivalent circuit is that voltage VAN. Yes, sir. Absolutely. What ZY? Exactly right. So ZY is Z delta over 3. So that's going to look like 9 plus J6 ohms divided by 3 is 3 plus J2 ohms. So we now know this quantity. It was correctly suggested that VAN is simply going to be our line current IAA times ZW plus ZY. So that would be 25.981 angle 10 degrees amps RMS. 3 plus 0.3 looks like 3.3. 2 plus 0.2 looks like plus J 2.2 ohms. Which I get to be 103.042 with an angle of 43.690 degrees. Volts RMS. And now we're ready to figure out what our phase voltages in our source are, or our line voltages in our source, because of the same thing. So how do I go from VAN to VAB? Multiply by √3 angle 30 degrees. Oh, crap. looks like 178.475 with an angle of 73.690 degrees. Volts RMS, which looks like what I got there. And then to get the B phase and C phase, we simply apply 120 degrees and 240 degrees. Any other questions about homework number 5? So you guys take a look at homework number 6. Use the class period right now to start working on things. And if you have any questions, by all means, ask about stuff. I want to be clear here. I have no problems literally working anything you ask of me. Or I can just pull random problems from this textbook and we can do that, but I figure it's probably a better use of your time to be working on the homework set and then asking questions about that.